Okay, I would like to welcome all of you back from the previous session. In this session, which is part 2 of the online review session for organic chemistry 2 final examination for the spring 2013 semester, I want to go over some of the problems that we were not able to do in the previous session. So in this session, we are going to start with problem 20 and go all the way to problem 30, and then from there we go to problems 51 to 55, and that will be the end of the session today. Okay, so let us go to problem number 20. Rahul, can you go ahead and read this question for us?
Which reaction sequence will not give benzoic acid as the major final product?
Okay, very good, and thank you. Okay, so for this problem here, they are asking which reaction sequence will not give benzoic acid as a major final product. Okay, so these are the reaction sequence here. They have benzonitrile, this here. This is benzonitrile. Okay, and then they do the hydrolysis of benzonitrile and then follow that up with acidification. Okay, let me ask you this. Will this give you carboxylic acid? Yes or no? This sequence. Okay, this sequence here. Okay, this will be yes. This is because you could hydrolyze a nitrite to a carboxylic acid either under basic condition or acidic condition to get the benzoic acid. So this will not be the correct answer here because this will give you a benzoic acid. However, this sequence, number 2. In number 2, what do you have here? You have phenyl magnesium bromide reacting with formaldehyde. This is formaldehyde, this molecule here. And then they follow that up with dilute acid. Will this give you benzoic acid? Yes or no? Will this give you benzoic acid? This is an aldehyde reacting with a Grignard reagent. Okay. Will that give you? No. An aldehyde reacts with a Grignard reagent to give you a primary alcohol. Okay, so here you get a primary alcohol. Okay, you guys, you need to know these reagents. A Grignard reacts with an aldehyde. In this particular case, this aldehyde here is formaldehyde to give you a primary alcohol. Now, if you have a regular aldehyde, then you get a secondary alcohol. But in this case, since you have formaldehyde, which is the simplest aldehyde, you get a primary alcohol. About this one here, okay, you have toluene. This is toluene right here. Okay, reacting with potassium permanganate with heat under basic conditions. Then you add dilute acid. Does that give you benzoic acid? Yes or no? Say yes. Okay, that answer is yes. Okay, does it give you a carboxylic acid? Yes or no? This sequence, does it give you a yes? Very good. This sequence will give you, in this case, you will get this. In this case, you get this product here. You also get benzoic acid. Because what the iodoform reaction does is to clip this here and then turn this carbonyl to a carboxyl group. So you get benzoic acid. So therefore, what is the answer here? What is the answer to this question? Okay, number 2. The answer to this question is number 2. Let's get all of this out. The answer is number 2. Right here. So this is the only one of this sequence that does not give benzoic acid. And that is what they are asking for here. So the answer is number 2. Okay, so we go to the next one. Okay, this should be fairly easy. Natalia, go ahead and read this for us.
Which one from the following compounds is not aromatic?
Okay, thank you, and very good. Which of these is not aromatic? Okay, we should be able to do this right away. Okay, what would be the answer here? What would be the answer here? Which is not number 4? Okay, very good. Natalia said number 4. Okay, so the answer here is number 4. Okay. The answer is number 4. Okay. Now, why number 4? That is correct. Why number 4? Natalia, why number 4? You could pick up the mic.
This is because of pi electrons, so it does not match with the Huckel's rule, or I don't remember his name.
Well, no, okay, not the Huckel's. Not Huckel's. It's because you do have 6 pi electrons here. But if you look at this carbon here, this is an sp3 carbon. Okay, so therefore, this ring system here, there is no complete conjugation, no complete electron delocalization, within the cyclic system. Because of this here, there is no p orbital here to allow this pi electron to delocalize over the complete range of atoms in the ring system. And that is why this is not aromatic. If you look at this here, this is aromatic. Number 3 is aromatic. It does have the same number of pi electrons as number 4. However, this carbon here is an sp2 carbon, which means that it has a p orbital. You have p orbital available here. You have p orbital available here that you could move the pi electron into. So there is complete electron delocalization right here. Okay? So anyway, the answer here is number 4. Number 4 is not aromatic. Somebody asked me number 19. Number 19, the answer for number 19 is 4. That was the answer to that. Okay, so let us go move on. Okay, okay, I believe if you are back, I think you are back. Your mic is working. Go ahead and read this question for us.
Which statement is true about the reaction of S2-bromobutane with hydroxide?
Okay, thank you, and very good. Okay, so this question is saying which statement is true about the reaction of S2-bromobutane with hydroxide. So this reaction here, this is S2-bromobutane with hydroxide. Which statement is true? The reaction proceeds with complete racemization. Racemization simply means that you are starting with an optically active molecule and you are ending up with molecules you are ending up with 2 molecules that are mirror images which essentially are not superimposable. In other words, you're ending up with 2 enantiomers. equal amount of enantiomers. That is racemization. Equal amount of enantiomers. That is what you mean by racemization. Okay? So what this question is actually testing your knowledge of the reaction mechanism. If you look at this reaction, what type of reaction mechanism is this? Is this SN1 or SN2 reaction? Is it SN1 or SN? Exactly. SN2. And you know SN2 reaction, what does it give you? What does SN2 give you? It gives you inversion of configuration. Excellent. Inversion of configuration. That is what an SN2 reaction gives you whenever it is appropriate, whenever you have chirality in the molecule. Inversion of in other words, if you start with a molecule that was S, you end up with a molecule that is R for the most part. That is what the SN2 reaction would generally do for you. Okay, giving you that information, what would be the answer here? What would be the answer here? Say, number 3, the major product is obtained is R2-butanol. Excellent, because you are going to form an alcohol. The hydroxide comes here, displaces this from the back, and the bromine leaves, so you are going to get an alcohol. So the answer here is this. This is correct answer right here. Number 3. Okay? Okay, let us go to the next one. Okay, Lorna, go ahead and read this for us.
In the molecule below, which site would nucleophiles attack?
Okay, very good, and thank you. Okay, in this molecule here, what they are asking, which site with the nucleophile attack? In other words, which of this carbon will be electrophilic? Which of the carbon will be electrophilic? Which is another way of saying which of the carbon will have a partial positive charge or will have a positive charge. Partial positive charge or positive charge. Because a positively charged carbon atom will be electrophilic. Okay? So, let us take a look at this. Which will be which carbon here will be electrophilic? C and D. C and D, 3. Okay. That is correct. Why C and D? Why C and D? That is correct, by the way, 3. Number 3 is correct. Why? Anybody has an idea? Okay. Because in D, you have the bromine atom here is more electronegative than the carbon atom, so it is therefore pulling electron away to itself. So this carbon will be partially positively charged. Of course, this will have a partial negative charge. So therefore, this carbon will be electrophilic. The same thing on this carbon number C. Also, this case, as a result of resonance, you could move the electron to oxygen and thereby creating a positive center on this carbon atom here as a result of resonance. So C will also be carbon number, this carbon here will also be electrophilic. Very good. Okay, let us see here. Okay, Makimba, I believe you are back. Your mic is working. Can you go ahead and read this for us?
The IUPAC name for the following structure is...
Okay, very good, and thank you. So this is a straight case of nomenclature. This is just knowing your nomenclature. So what would be the answer to this? You should be able to do this right away. What class of compound is this? Okay, what is the answer? Okay, number 2. Okay, you say number 2, which is 2-bromobutanoic acid. Yes. 1, 2, 3, 4. This is a butanoic acid. So the answer is this here. Very good. Okay, so this is a straight case of nomenclature. Okay. Okay, Natalia, go ahead and read this for us.
Which hydrocarbon, when treated with H2O and the following, produces butanol?
Okay, very good. So which hydrocarbon, when treated with water, mercury sulfate, and sulfuric acid, produces butanol? Okay, so therefore they are asking any one of these here, if you have this reagent, water, mercury sulfate, and sulfuric acid, okay, okay, which will produce butanol? Which will produce butanol? In this case, it could be this here, butanol. Okay, so which of these compounds here will do that? Okay, this is another case of knowing. Okay, 2-alkyne, yes. Okay, very good. Number 2, that okay, good. So this is this here. That is correct. Because anytime you have a carbon-carbon triple bond and you have this reagent here, this reagent will transform a carbon-carbon triple bond to a carbonyl of a ketone. Okay, in this case, because it is an internal alkyne, so you are going to, one of these carbon becomes a carbonyl and the other becomes a CH2. So this case, that is why you have CH here, butanol. Okay, so the answer is 2. Very good. So you need to know this reagent. I know it is a long time that we use this reagent, but you do need to know all of these reagents. This reagent will transform a carbon-carbon triple bond to. Okay, okay, let us see here. Rahul, can you go ahead and read this question for us again?
The following methods cannot be used to produce the following amide.
Okay, thank you. Okay, so what this question is asking again, say which of the following methods cannot, okay, certain cannot be used to produce the amide, this amide right here. Okay. Okay, in this case you have benzoic chloride. This is benzoic chloride. Here you have benzaldehyde right here. That's this C6H5 is actually this here, so let me write it out for you. Okay, this here is, of course, the aldehyde. Now, the question is, okay, the question is which of these methods cannot be used to produce this compound here? Anybody has an idea? Oh, this is a secondary amide. Okay, somebody say number 2. Number 2. Okay, okay, that is okay. Number 2, that is correct. Number 2 is correct. Anytime you, in this case, you have a primary amine reacting with an aldehyde. Anytime you do that, what do you get? You get an amine. You do not get an amide. Okay, so therefore, number 2 is correct. You cannot use number 2. So number 2 is correct. You cannot use number 2 to produce this secondary amide. Okay, because essentially The rest of this reaction here is what we refer to as the nucleophilic acyl substitution reaction. This primary amine will react with benzoic chloride to give you this product. This primary amine, which is methylamine, will also react with an ester, methylbenzoate, also to give you this product. And the same primary amine, methylamine, will react with an anhydride. This is an anhydride. Anhydride. And each one of these reactions will be a nucleophilic acyl substitution reaction. Okay, so the answer here is 2. You cannot use 2 to make this compound here. Okay, let's see here. Let's see who is here now. Okay, if you have not spoken tonight and your mic is working, can you go, in this session, can you go ahead and read this question for us? Anybody? Okay, okay, let us see here. Yeah, Lorna, go ahead and read this question for us. Question 4. Go ahead.
Which reaction will give the following compound after aqueous workup?
Okay, thank you. I'm very good. Okay, so here, this is a case of trying to see whether you know your reagents and also, of course, the reaction mechanism. So what we have here, which reaction will give this compound here after aqueous workup? What do you have? You have a Grignard reagent, phenyl magnesium bromide, the same Grignard reagent, another same Grignard reagent. Okay, now reacting with, in this case, reacting with acetaldehyde. Okay, whenever you have a Grignard reagent reacting with acetaldehyde or with an aldehyde, what kind of product do you get? What kind of product do you get? We did that before. You get a secondary alcohol. Okay, so this will give you a secondary alcohol. So that cannot be this here because this is a primary alcohol. Okay, so whenever you now have this Grignard reacting with ethylene oxide, okay, essentially this will displace this here, open up the epoxide, and then once you do your aqueous workup, okay, you get this. That's what the Grignard will do with ethylene oxide. Okay. Okay. Here, the Grignard does not react with an ether. Here, no reaction. This is an ether. Grignard does not react with an ether. And of course, here, the Grignard reacting with an alcohol, what are you going to get? You are going to get this. The Grignard in this case will react as a base to pull off this proton on the alcohol. And that is why you do not do a Grignard in the presence of an alcohol. So here you are going to get this. Okay, so it will essentially react as a base, and in the process you form methoxide. Okay, so therefore, what is the answer here? What will be the answer? Number 2, exactly. The answer is number 2. Which reaction will give? Yes, the answer is number 2. Number 2 will give the desired product, which is this here. Okay, so the answer is number 2. Okay, so moving right along, let us go to, okay, will you go ahead and read this for us?
The first step along the reaction pathway in a base-catalyzed aldol condensation is?
Okay, thank you. Okay, so now another case of checking your knowledge of reaction mechanism. Okay, they say the first step along the reaction pathway in a base catalyzed aldo condensation is, so what is the answer here? We should be able to do this right away. What is the answer? Okay, you guys already got that too. That is correct. The first thing you do in a base catalyzed aldo condensation is the formation of the nucleophile. Okay, you abstract the alpha proton. That is correct. So the answer here is this. Very good. Go to the next one. Okay. Okay, Natalia, go ahead and read this for us.
Which set of the reagents will give this product in the step after a suitable workup involving neutralization?
Okay, thank you, and very good. Okay, so what they are asking here, also once again testing your knowledge of the reagent and also testing your knowledge of reaction mechanism. So they say which set of reagents will give this product here in a one step after a suitable workup involving neutralization. Okay, good. So what is the answer here? What do we have? Okay, what do we have here? We have, this is what we need to form. We have the acetyl anion reacting with this. No. Okay, acetyl anion reacting with the ketone. Okay, so what would be the answer? Number 2. You guys said number 2. Number 2 is correct because in essence, this will be a nucleophilic addition reaction. Nucleophilic addition to a carbonyl function of a ketone. So in essence, this here, attack this. This goes here. It's a nucleophile. The acetyl anion is acting as a nucleophile, and then you get this. So this is a classic case of nucleophilic addition to carbonyl. And then you have this here. And then once you add the acid to this, that is what they mean by a suitable suitable workup involving neutralization, because you are adding acid to this, and so you now get this. Okay, hydronium ion comes here, abstract the proton from hydronium ion, and then you get your product. And this is the product right here. Okay, so the answer here is number 2. The rest of them will not work. Okay, the answer is number 2. This is the correct answer here. Okay. Okay. Okay, let us now go to question number 30. Okay. Let me see here. Makimba, go ahead and read this for us. Okay, if Makimba is not ready, let me see here. Who else is here? Okay, Rahul, go ahead and read this for us.
Is the major product of the following thermal reaction?
Okay, thank you. I'm very good. Okay, so what they are asking you to do here, okay, what is the major product of the following thermal reaction? In other words, this reaction, once you apply heat, okay, once you apply heat, what is the product? Now, let me ask you guys, what kind of reaction is this? There is a name for this reaction. Diels-Alder reaction. Excellent. This is a Diels-Alder reaction. Diels-Alder reaction. Very good. Okay. So, what is the answer here? What would be the answer? Number 3. Number 3 is correct. Okay? Number 3 is correct. Okay? Because you see here, you see this part of the molecule here, this here, that is this part right here. Okay? Of course, you are forming a 6-member ring, and this part of the molecule, which is right here, okay, this here, and that is what this here is. Okay? And then the 6-member ring that you form, that is the rest of the molecule right here. Okay, because Diels-Alder reaction gives you a 6-member ring. If you have this, for example, and you have this, and you do a Diels-Alder reaction, you form a 6-member ring right here. That is what the Diels-Alder reaction gives you. Formation of a 6-member ring. And here you form the double bond is now big. You have the diene, this is what we call the diene, and this is what we call the dienophile. Now in the final product, this is the adduct, which is the final product of the Diels-Alder reaction. The carbon-carbon double bond will now be in the position where the original carbon single bond of the diene was. Okay, if you say this is carbon 1, carbon 2, carbon 3, carbon 4, and that will be this here 1, 2, 3, 4. You notice that the new double carbon-carbon double bond is now between carbon 2 and carbon 3, which was where the single bond was originally. Okay. Okay, now let us do this. After we do this, then we move to question 51. Okay, let us see here. Okay, only go ahead and read this first. Okay, it's not ready. She must be having problems with her mic. Yeah, go ahead. Can you read that again?
Okay. A phenol is a substance that contains...
Continue. Okay, very good. Okay, very good. A phenol is a substance that contains an OH group attached to a benzene ring, two benzene rings joined by an oxygen atom, and OH group attached to a double bond of an alkane, number 4 choice, and OH group attached to an sp3 hybridized carbon. So which is the answer here? Number 1. So this is very simple. Number 1. A phenol is a molecule in which you have the hydroxy group is attached to benzene. So this is your phenol here. Okay? And happens to be the name of the class of compound. It also is the specific name for this molecule. This is a phenol. And this particularly called phenol, this molecule here. Okay, at this point, let us now go to synthetic design. Question 51. I think we've had enough of multiple choice by now. Okay. Okay, Lorna, go ahead and read this for us.
Starting with a Diels-Alder reaction, then followed by a Michael addition reaction and other appropriate reactions, provide a synthetic scheme for the following compound. Okay,
very good, and thank you. Now, what they want you to do here, since we have now left the multiple choice questions, we now get into synthetic design. Now, they want you to make this compound, okay, and then to make this, they also want you to use a Diels-Alder reaction, Notice there is no restriction on what starting material you can use, what reagents you can use, as long as you use a Diels-Alder reaction. Okay, now if you take a look at this molecule here, you say, okay, we know we are going to make a Diels-Alder reaction. Diels-Alder could give us a 6-member ring. So I would say maybe I could make this ring here from a Diels-Alder reaction. Okay, so therefore I would say maybe I could use this as my diene. So if I do that and I want to form a Diels-Alder reaction, that simply means that I must use as my dienophile this here. Okay. Then I also see another part of this this problem. Now you wanted to also make. They also wanted to make this primary amine. So now the question is, how do I make a primary amine? Okay, can anybody give me a couple of methods for making primary amine? Or just maybe more than a couple. How do you make a primary amine? Michael addition. Oh, okay. Reduction of reduction of reduction of nitrile. That's a good one. If you take a nitrile, you could reduce a nitrile using LAH followed by adenine ion. You form a primary amine. Okay, that's a good one. So if you keep that in mind, so we want to form this primary amine. So what you then want to think of, maybe you are starting with a nitrile. If that is the case, okay, how do you form a new carbon-carbon bond? Somebody said earlier we need to use a Michael. That is excellent. That is correct. Who said that? Somebody, I've forgotten who said that. Said we need to use a, but that is correct. So that means, therefore, when you do your design, there must be a carbon-carbon double bond here. Okay? Because you want to do a Michael addition of a nitrile to the beta carbon. So, if I do my Diels-Alder, okay, that gives me this. So you finish your analysis, and then you want to begin to put the pieces together. So that is give you this. The double bond is now going to be here, okay, from your Diels-Alder, and this is still here, okay, and then you will then do a Michael addition, step 1, then followed by adenine ion, and that gives you this. Okay, so that gives you that, and this here. Okay, now at this point, what do you now do? You could now do this. You could now do LAH, followed by dilute acid. That will transform this nitrile to the primary amine. That gives you the primary amine. Now you see, okay, now, you know, yeah, okay, now let me say this. You need to protect, okay, you protect this first, not as simple as that. Let me back up on that. You need to protect this. Okay, I want to protect this here. With this here, with a keter, okay, you protect that, okay, so now you have this. Okay, before you do the before you do the lithium aluminum hydride reaction. Okay, so let me take this out of here. This is still here. Okay, now the double bond is still here. Now once you do that, now you could now do your LAH reaction. Step 1, LAH. Then step 2, hydronium ion. Now you get your primary amine. Okay, now once you do that, okay, I'm sorry. Once you add the dilute acid here, this will open. Once you add this dilute acid here, of course the ketal, your protecting group, which is the ketal, will open up. Now you have this, and then finally you can now reduce this with hydrogen in the presence of palladium or platinum to get this here. Okay, so that is how you are able to go from, how many steps do we have? From the Diosada, this is 1 step, 2, 3, 4, and 5. Okay, now you get to your final product. Okay, now if you all see that, give me a happy face. Okay, very good. So keep in mind when you get to synthetic design, now you now begin to use your knowledge of those reagents, okay? Use your knowledge of those reagents. Okay, let us go to the next one. Okay, let us see here. Okay, Natalia, go ahead and read this for us. Number 52.
Provide a synthetic scheme for the following transformation.
Okay, thank you, and very good. Provide a synthetic scheme for the following transformation. And what is that transformation? We're going from an ethylbenzene, we want to form this amide, a secondary amide. This is actually an amide of acetic acid. Okay, so what do we need to do here? Somehow, we need to remove the carbon-carbon bond to the benzene molecule and replace with carbon-nitrogen bond. So what kind of reaction do you think we need to do here? Okay, Ebra is giving us some suggestions. Natalia giving us some suggestions. Yes, let me follow your suggestion. What you guys are saying we do a potassium permanganate dilute acid sequence that gives us the carboxylic acid. Okay, somehow I don't know where you want to go here, but it sounds good to me. Okay, now what is the next step? Okay, I'm following your step now. Both you and Natalia and Ebra. Okay, now you say that we need to do thionyl chloride. Okay, step 1, thionyl chloride. That will form the acid chloride. Then step 2, ammonia. Very good. I see where you want to go now. I see exactly where you are going. So now you form a primary amide. Okay. Now once you do that, then what do you do? Okay, then you do your Hoffman. Okay, very good. Okay, I am following you guys' steps. Okay, Br2 with base. This is Hoffman rearrangement. Okay, so that will now give you your aniline. Okay, I think I know where you guys are going with this. So you now form your aniline. Let me take this. Doesn't look good here. You form aniline. Okay, so now where do you want to go from there? Okay, now you form aniline. What is the next step? What is the next step? Keep in mind, this is where we want to go. we want to form the amide of acetic acid. Okay, very good. So now you say now you want to do this. You want to perform a nucleophilic acyl substitution reaction using the acetyl chloride. Okay, very good. And once you do that, that takes you to this here. Okay? Okay, if you follow that, give me a happy face. Okay? So you really, this is a case, at this point, we have now gone beyond knowing your reagents. We are now beginning to use our critical thinking skills to put together a synthetic design. But if you do not know those reagents, you cannot do this, okay? So please, you need to know those reagents. Okay, so let us go to the next one. 53, okay. Lorna, go ahead and read this for us again.
The reaction below is an electrophilic aromatic substitution. Provide a mechanism for the transformation.
Okay, very good, and thank you. So this reaction here, now this is the first time we are now dealing with a reaction mechanism. They say it is an electrophilic aromatic substitution. So what is the reaction? What is the mechanism of this reaction? Okay, you have a carbon-carbon double bond, and then the final product is we have forming tertiary butyl benzene. We have forming tertiary butyl benzene, and they have also told us that it is an electrophilic aromatic substitution. So therefore, in order for you to perform this reaction, you need to form an electrophile. So since we are adding this, that means somewhere down the road, we need to form this electrophile. So that means we need to form this electrophile, okay, before this reaction will take place. So how do we, okay, I see now. It says HCl reacts with double bond to Markovnikov addition. Excellent, excellent. Okay, now I got the answer I was looking for. Okay, so we start with this here. The first thing you want to do here is to form your electrophile. Okay, and HCl adds to isobutylene right here. Okay, HCl adds to that in a Markovnikov addition. So now you have okay. Now, once you form this here, now you now come to your benzene, because you are told to give the complete reaction mechanism. Come to your benzene. So now the benzene will now have, does it have, you have this pi electron here, attach the electrophile, and then once it does that, by the way, you know that you have a chloride here somewhere. Okay, once it does that, what do we have? We have this. So say that this is here, this is here, this is here. We see have this hydrogen here, and we have this hydrogen here, and the positive charge is here. So now what is going to happen now? What is going to happen now? Okay, the chloride comes in and abstracts this proton here. Very good, excellent. I'm glad you guys have not forgotten the mechanism of electrophilic aromatic substitution. Abstract this proton, and then the pair of electron comes here to form a carbon-carbon double bond, thereby regenerating the aromatic ring system. So now you have this. Okay? And that is what they ask us to do, and that is what this is. And that is what this is right here. Okay, so we have now given the mechanism of this reaction. Okay, so far so good. So I think we will be out of here within the next 10 minutes. That is good. Let us go to 54. We have 2 more problems to solve. Okay, let us see here. Natalia, go ahead and read this for us.
The reaction of benzoyl chloride with the methylamine is a nucleophilic substitution reaction. Provide the product in the reaction mechanism.
Okay, very good. Actually, we did this, I believe, in exam number 4. Okay, but this should be a fairly simple one. Once again, testing your knowledge of the reaction mechanism. So you have benzoyl chloride. Okay, then you also have methylamine. Okay, so the methylamine acts as a nucleophile because this is a nucleophilic acyl substitution reaction. This pi electron goes to oxygen. This is a classic case of nucleophilic acyl substitution reaction. So now you have this. And that is how all of these nucleophilic acid substitution reactions, how they occur. You have this here, and then you have this here. Okay, whenever you are giving reaction mechanism, you need to account for all of the electrons and all of the atoms. So now, what happens, we are going to regenerate this here. Carbonyl will reform, and once you do that, the chloride will live as a living group. Okay, so now we have this. Okay, let me be consistent here. We have this here, and this here. And then we have this. We now have this. Okay, the nitrogen is positively charged. Of course, you have the chloride here that was released. Now the chloride now comes in and grabs this proton here, releasing the pair of electrons to nitrogen, and therefore you get to your final product. Okay, plus HCl. Okay, so that is the product of this reaction, and also we have given you the mechanism. Okay, so finally, let us go to the last question of the day. I think by now everybody is ready to go home. Okay, let us see here. Okay, Rahul, go ahead and read this for us.
Provide a mechanism for a Robinson annihilation reaction.
Okay, thank you, and very good. Now, what they want you to do here is to provide a mechanism for Robinson annihilation reaction. You notice here they have not given you any limitation as to what you can use for this. So the only thing you need to know here is Robinson annihilation reaction is equal to a Michael addition followed by an intramolecular aldo condensation. That's all you need to know. Now, if that is all you need to know, then you could do just about anything you want, okay? Okay, I'll keep in mind Robinson annihilation. Since you are going to do an intramolecular aldo condensation, you are going to form a ring system. Annihilation means forming a ring. So let us use this. I will say, okay, since there is no limitation, I could start with this. Okay, I start with that molecule. I say, okay, I take hydroxide, okay, in ethanol, or, yeah, for the most part, you use hydroxide in ethanol. What is the first thing that will happen? We form a nucleophile. Okay, deprotonate that alpha carbon there. And then, what do you think I need to do now? What do you think I need to do now? What do you need to do? Anybody has an idea? Now I form my nucleophile now. Keep in mind what Robinson annihilation is. Okay, do a Michael. So I need to then use an appropriate Michael acceptor, which would be an alpha beta unsaturated ketone or aldehyde. In this case, I need to use an alpha beta unsaturated ketone because I want to eventually do an intramolecular aldo. Okay, so that gives me this. Because now you are going to get this. This comes here, and this electron goes to this alpha carbon. So that gives us this. And then we have this. Okay, so at this point, we are now going to protonate this enolate ion here. So that gets protonated by the solvent. Okay, so now we have this. Oh, I'm sorry, this is here. Okay, okay, then this is here. Okay, so now we have this. And this is here. Okay, at this point, let me get this out of the way so I make myself some room. So what have I done? At this point, I have done my Michael. I've done the Michael now. Now, what do I need to do now? What do I need to do next? Now that I've done the Michael. Anybody know what I need to do now? Okay, now I do my intramolecular aldo. Okay? Okay, so now what happens? Okay, since you have the hydroxide in solution, we could still go ahead and use the hydroxide. Or the ethoxide you could use also. This comes in, abstract this proton, and this electron goes to this carbon here. So what do we now have? Get this out of the way, doesn't confuse us. So now what do we have? We have this. Now from enolate on that. Now the enolate now comes in, attach this here, and this part, at this point we want to do our intramolecular aldo. Now we have this. And this is here. This is here. Okay. Now, finally, now I want to keep in mind now this comes here. Of course, forms water. Since we have sucked this proton from here to form this, so we could now think of a situation in which this alkoxide comes here, pulls off the proton from water, and then we have this. Ketone is here. At this point, we have formed our aldo. And then finally, we then apply heat. Okay, you apply heat and then we form this here. For my alpha beta. And what you've done here, this is the aldo condensation right here, intramolecular aldo. Color my pen. The intra molecular aldo condensation, and then this complete process here is what we refer to as the Robinson annulation. Keep in mind, Robinson annulation is a combination of Michael addition reaction followed by intramolecular aldo condensation. Folks, unless you have a question to ask me, we have come to the end of our session today, and indeed the last session of the online review sessions for the spring 2013 semester. So I will see you guys on Tuesday. And so unless some of you want to stay around for another 5 minutes to ask me further questions, enjoy the rest of your evening.